I will go to the last lecture of week 6, and in this lecture I will summarize briefly what you learnt in week 6 and do some practice problems. And I want to emphasize that I will just do them rather in a quick way, but you should go back and you should work them out in more detail. Okay. So, week 6 lecture 5, summary of week 6 and practice problems. So, to summarize what you learnt in week 6, we learnt about the 32 crystal class and we learnt the Schoenflies notation. We learnt the Hermann-Mauguin notation, we learnt the long form and we learnt the concept of unique operations. Okay, that helped us to write the Hermann-Mauguin notation. Then we learnt about the short form of the Hermann-Mauguin notation, okay, where we used lot of ideas from combination of symmetry operations, okay, and how combination of symmetry operations implies presence of other symmetry operations. And finally, we looked at the Hermann-Mauguin notation for the space groups. Okay. So for all the 230 space groups, okay, we didn't list all the 230 space groups, but essentially all these space groups have a Hermann-Mauguin notation and we briefly saw some of the features of that. Okay. And again I can emphasize that there are certain websites that which have this thing explained. Okay. So, this is a website where they have this is a course website where one of the links talks about different crystals and it gives all the space group and the symmetry operations. And then this is an excellent resource for getting the space groups at very high resolution. So just by giving the number of the space group, you can get the space groups at very high resolution. And then there is the International Tables of Crystallography, okay, which unfortunately is not a free resource. You have to purchase it, okay, but it's the defining resource for a lot of these details. Okay. So if you have an arbitrary crystal and you have the symmetries and you want to know what space group to classify in it in, then you can look at the International Crystallography, International Table of Crystallography, and find out the exact symmetry operations for each space group, and check with your material and put it in the appropriate space group. Okay. Now, let us work out a couple of fairly simple practice problems, okay. And again I encourage you to go and put these I mean, for example, FCC, BCC, HCP, you can try to look in these in some of these resources and try to actually see what the space groups look like, okay. So, identify space groups corresponding to the following crystals: a monatomic FCC, monatomic BCC and an HCP crystal, okay. So, let us start with the monatomic FCC. Okay. Now, the short form of the point group, okay. So, the point group we already saw was octahedral, okay, with 48 operations. Okay. It's a cubic crystal system, okay, and the point group had a notation M 3 bar M. So, now the space group in this case, okay, the space group in this case is just F M 3 bar M. Okay. In other words, there are no additional glides or glide reflections or screw axis. Okay. So, the space group notation is just F M 3 bar M. What about the BCC? Now, the BCC, okay, again it is M 3 bar M, okay, and there are no additional glides or screw rotations. Okay. So, the space group is just I M 3 bar M. Now, what about the HCP? In this case, we need to inspect the point group. Okay. So, actually the point group is 6 by M M M. So now what about the space group of HCP? So HCP, okay, space group, okay. So let me do this in a slightly different way. So I'll put a few. We have all these four up to a maximum of four symbols that we have to put. Now clearly the first one has to be primitive, because in the hexagonal we saw that only primitive is allowed. Okay. Now what about the 6 axis by M? Okay. Now we saw that in the HCP has a screw axis. In fact, it is a 6-3 screw. Okay. And it has a, and the 6-3 screw axis has a perpendicular mirror. Okay. So you have a 6-3 screw axis and a perpendicular mirror. Now the second position, okay, has to be perpendicular to the first position, and it is one of the symmetry directions, and this you can show is just a mirror. Now the third position is in between the secondary mirrors. Okay, so you have the 6 mirrors in the secondary. Actually it will be now. You will have these mirrors that contain the 6-3 axis. Okay, and now between those mirrors there is another mirror reflection. It is not exactly a mirror reflection, but it is a C glide reflection. Okay, so if you look at the hexagonal, if you look at the planar representation of the HCP, okay, so you have the hexagonal lattice, and you have these additional points at z equal to half. So this is z equal to half, and this is z equal to 0. Okay, and you can see quite now you can see that there will be glide reflections, okay, which will take one of the green points to one of the blue points. Okay, so there will be a C glide reflection mirrors. Okay, that will be the third position. Okay, so the space group of HCP is actually P6-3 by MC. Okay. And its number, if you in the crystallography table, is 194. Okay, so its number is 194. Okay, and it has a total of 24 symmetry operations, which is actually the same as the. I mean, if you look at the unique operations, okay, there are only 24 of them. Okay, so these are the space groups of the HCP crystal. So what is important? Okay, so the 6-3 axis was obvious, but again you can easily see that it should have a glide reflection. Okay, and if you look at the third position, okay, the glide reflection of interest has to be a C glide. Okay, again it is important that this is only for the third. If you look at other positions, then you can have different glide reflections. Okay, you might not have a C glide. Okay, so clearly if you have a mirror like this, okay, that would be a C glide. Okay, something like this would be a C glide plane. Okay, and then there would be equivalently there would be other mirrors also. Okay, so it will take a mirror like this will take this green point to a glide reflection. So it will take it on top of this blue point. Okay, next problem, identify the space groups of the diamond and the zinc blende crystal structures. Okay, now this is substantially more complicated, okay, and especially the diamond. Now the point group of the diamond crystal, okay, is the following. Okay, so we will start with diamond. Okay. Now this is in the M3 bar M. Okay, so that is the cubic system and the hexoctahedral class, crystal class. And if you, in addition to these, okay, we notice that I mean, in case of diamond, okay, there is a diamond glide, and a 4-1 screw axis. Okay, so these are the two translational symmetry elements that are there in the diamond crystal. Okay, you recall. Okay, so a point to recall is that either of these, either the diamond glide or the screw axis, okay, these can generate the entire crystal. So both the diamond, so either of these can generate entire structure. Okay, and to see this, okay, so we saw this when we were doing when we are seeing the screw axis. We saw that if you imagine if you look at the diamond cubic structure, okay, in the planar representation, and I'll take I'll show the entire cube, okay, and you imagine that you have points at, so this is z equal to 0, then you have points at z equal to 1 by 4, z equal to half, and finally at okay, and now we know very well that there is a screw axis of rotation. Okay, in fact there are several screw axis of rotation. Okay, and you can show, for example, you can easily show that there is a 4-1 screw axis, okay, that passes through this point. Okay, let me show it in a different color. So this is a 4-1 screw axis. Okay. Okay, so we have this 4-1 screw axis, and similarly you have several other screw axes in diamond. Okay. Now what we said is that if you take this 4-1 screw axis, okay, so this is actually a 4-1 screw axis. So what it will do is it will take, if you operate once by this 4-1 screw axis, then this black point will go to the light blue point, which is at a higher, so it corresponds to rotation by 90 degrees, and then it will be raised by 1/4. Okay, so it will come to this point. Okay, and you can go ahead and you can do this, and then the next time it will come on top of this and so on. Okay, what you can show is that if I show it on this big figure, okay, and let me use a slightly different, let me use this purple color. So this was that point in black, okay, and if you do one of these screw operations, so you have a 4-1 screw axis here. Okay. And what this 4 1 screw axis will do is it will take this point at z equal to half, rotate by 90 degrees and raise by 1/4. So, it will come here. Okay. And what you can see will happen is that this blue point will go to this green point. Oh, in fact what I am showing is something slightly different. I am showing this blue point will go to this green point. Okay. And if you again put if you again apply this screw rotation, okay, then you will see that you will end up at this point. Okay. And this will keep going on. Okay. Now, there are other screw axes also in the crystal. So, there is a 4 1 screw that is there here. Okay. This will also generate the remaining points. Okay. So, what you see is that if you have a 4 1 screw, okay, and this mirror, okay, then you can generate the all the other points. Okay. So by operating this 4 1 screw multiple times, you will find that you can generate all the required lattice points. Okay. Now, again there will be a 4 3 screw here, and another 4 3 screw here. Okay. But you keep in mind that that the asymmetric unit of diamond has 8 atoms in the crystal. So, the asymmetric unit, okay, we only need to consider one of these, okay, one of these as the asymmetric unit. Okay. So you can just take 1/8 of this cube for the asymmetric unit. So, for example, you could take this as the asymmetric unit. Okay. And now we will have to put the other screw axis here and here. Okay. Okay. So, with this screw axis, we can generate the other points in this asymmetric unit. Okay. So, similarly, the glide plane can also be used to generate several other symmetries in the several other points. Okay. So, to make the long story short, okay, we will say that in diamond you have an M 3 bar M. Okay, this is the point group. Okay. Now, clearly it is the space group. Okay, since it is face centered, you have an F here. Okay, and now the first space you can have you have a 4 1 screw axis, but we saw that the 4-fold axis is a consequence of the 2 mirrors. Okay. So, what we can do is that you still have to have the 3 bar. Okay. Now, if the third mirror is actually a glide mirror, and now because you have the glide, okay, the glide will generate the 4 1 axis. Okay. So, but there is an additional operation, that is the diagonal glide. Okay. So actually the first position corresponds to the diagonal glide, then you have the 3 bar, and then you have the C glide. Okay. So, these 3 will generate the space group of diamond. Okay. Now, what about zinc blende? Okay. Now, in this case you do not have the full symmetry of the cube. In fact, the point group is 4 bar 3 M, and in this case the space group, okay, space group again it is face centered, it is just 4 bar 3 M. So, there are no glide operations or no screw axis. Okay. So, one more example, okay, and then we will conclude this week. Okay. So, this is explain the class of the space groups, and I have given 3 space groups. I have called one I 4 1 by AM 4 1 by A MD, C MCA and F 4 bar 3M. So, identify the class of these space groups. So clearly now let us look at each of them. So we look at I 4 and subscript 1 by A MD. Okay. Now, the 4 at the first position implies okay. So this could mean either cubic or tetragonal. Okay. In this particular case, okay, so you have an A glide and a D glide and you have a 4 1. Okay. So, we saw that in the cubic, okay, you can never have this kind of combination. So, this is actually tetragonal. Okay. So in a cubic, if you the middle index has to be 3 bar. Okay. So, you cannot have an M here. The 4 at first position implies either cubic or tetragonal. So, this has to be tetragonal. Similarly, if you look at C MCA, okay, now there are 3 mirrors. Okay, so there are 3 mirrors and you can have a C centered. So, this has to be orthorhombic. What I should say is the crystal system. So the crystal system is orthorhombic, the crystal class is MCA. This is the crystal class is just 4, actually the crystal class is MMM. Crystal class is MMM. Here the crystal class is 4 MM. Okay. Now, the last case you have F 4 bar 3 and here this is since you have a 3 at the second position, it has to be cubic, okay, and the crystal class here is just 4 bar 3. Okay, so, this is the crystal class. Okay. So, with this I will conclude week 6 of this course. Okay. So, what you see is that from the space group notation you can say whether you can at least identify the crystal system and you can say whether it is face centered, body centered or what kind of centering it has. So, this information at least you should be able to identify given the space group. Okay. Now the other details of which crystal class it belongs to or exactly which what are the details of the space group, that is much harder. Okay, and that is typically we refer to the tables to find that out. Okay, but at least the basic crystal system and whether it is and the centering should be easy to infer from the name of the Hermann-Morgan symbol for the space group. Okay, so I will conclude week 6 here, and then in the next week we will start talking about defects in crystals. Thank you.